And
Was that for Astronomy Cast or for
no, just on
Space
my channel.
Hangouts?
Yeah.
Oh, cool.
Oh, let me shift everybody around here. It was a NIAC. It's I every time the NIAC grants come out, I sort of chase down each person in the NIAC awards because nobody else. It doesn't seem to occur to anybody else to chase down all these stories, and each one is just like so cool. It's like I'm talking to the future. I love that. I
Awesome.
think the NIAC is like my one of my favorite things that NASA does.
What
The
is the Naya?
the NASA is their Advanced Innovative Concepts Lab, and so they hand out about 15 prizes between sort of 25,000 and $5 million every year to a bunch of different technologies depending on their level of technological readiness. And the the ideas have to be crazy but not too crazy. And so like if your idea isn't crazy enough, you won't get funded, right? And if your idea is too crazy, then it won't get funded. But David Kipping, I'm surprised. Have you considered throwing in for a NIAC prize for like the Terrascope or any of that?
Um, it's crossed my mind. We have something similar in house at Columbia at a smaller scale
Yeah.
that I've been thinking about trying. It's called Rise, and it's like an internal grant. So that would be my logical next step. But I'm not an instrument builder, so in that sense, it would be I'd probably need to collaborate with many people to make that happen, I think.
Yeah, yeah. Yeah, I mean, I think like it's sort of good promotion. It sort of puts things into the pipeline as they sort of move up the technology readiness scale of NASA. But I think it's a great program. I really like it. I've had a chance to talk to the director and the it's just it just feels to me like that's NASA's best role is to take on technological uncertainty, take on technology risk that companies can't afford to weather yet, and then they de-risk the idea, and then other people can take it farther. And when you think about all of the modern rocket technologies, it's all just in space exploration. So many of the technologies are just NASA was willing to take the risk. Ion engines, just there's a million of them, and
Yeah.
Where's the space elevator? Somebody start
there's
getting that
there's
space
there's
elevator
been
going.
space elevator concepts in NIAC in the past.
Well, you probably know about the Jet Propulsion Laboratory used to have the breakthrough the breakthrough lab, it was called, I think, breakthrough propulsion lab. And I remember as a kid reading about that lab and being like so inspired to want to work at NASA.
Yeah.
And these guys were like literally calculating things like about warp drives, and
Oh,
there was
right.
actual funding for this within NASA. It was wild, and they
Yeah.
closed it down. I think like
Yeah, that
maybe
was under
5-10 years
Bill.
ago or so.
That was under Pete Worden at NASA Ames.
Yeah,
Yeah.
yeah, I think you're right. Yeah,
Yeah.
but
Cool. We're live, by the way. I, I didn't I
Man,
didn't
I wish we
mention.
still gave money for things like
just
that.
slip
That's
that
like the
in.
coolest lab. That sounds like the coolest place. I want to go visit in like 5 years in the past.
Yeah, they had last time I was down in Silicon Valley. This was like I don't know, like maybe 8 years, 7 years ago. They they had recently bought a quantum computer with Google, like just to figure out how it works.
That's neat.
That's cool.
Yeah, yeah. And so they just absolutely are testing out all these really cool advanced techniques, as you say, warp drives, just trying to explore them and figure out if they actually are possible. So,
It's aspirational and inspirational to, when you read about that and you're thinking about maybe being a scientist one day and you hear that there's a place for that, even if
yeah.
it's still niche, it really does inspire people, I think.
Well, and the part that amazes me is that if you go back and look at old NASA proposals, if you read like old NASA history documents, some of the old stuff, even back in like the 50s and the 60s, all of the stuff that's happening now, they had predicted. Like the original space shuttle, if you go back to the original space shuttle designs, it's the Starship with the Super Heavy, right? It was a two-stage reusable rocket. Both stages would launch vertically, and then the booster would fly back to Earth and land on a landing pad. And then the orbiter would keep going, and then it would make it to space, and then it would orbit around, do its mission, and then it would return through the atmosphere and land just like the space shuttle. And so but they couldn't do a vertical landing because the computers just weren't powerful enough to handle that kind of thing. And so,
Dinosaur was an interesting early,
Dinosaur,
up. That was from the early '60s,
right? Yeah, and then even they had tested like vertical takeoff and landing back in the early 2000s, so like 15 years before SpaceX. A group had already demonstrated vertical
the idea
rocket
for the original Orion using atomic bombs to get up to about a tenth of the speed of light.
I don't know about that.
It's crazy stuff, but it was.
I was going to mention that.
Yeah.
Isn't there an XKCD that's like anytime somebody talks about space travel, you eventually will converge onto Orion. Like you'll always start talking about it.
I think they wanted to look at how they could do interstellar travel with no like technological breakthrough with the technology they had in the 60s. That was the design concept. So it's kind of out there, but it didn't require any kind of new innovation. They knew how to blow up.
Yeah.
They knew how to blow up atomic bombs.
I think it was just a way to justify building a lot of bombs. All right, we should do our show. Okay, I'm going to put you guys all back in your boxes, and we will begin.
Talk about today's science.
Yeah, or we could just not. We could just chat. It'd be fun. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, March 10th. I'm Fraser Cain, publisher of Universe Today. This week, we're going to be talking about using super lasers. I don't even want to say any more. To understand the super Earth mantles. How fast is the universe expanding? We have a new answer. Rocket Lab has a new rocket and an origin for the moons on Mars. Joining me today on my screen right now, I've got Dr. Kimberly Cartier. Kimberly.
Hello. Happy podcast day.
Happy podcast day to you too.
And greetings, Sky people, as we discussed last time I was on the show.
We've also got Dave Dickinson. Oh, our special guest.
I got a distress call from Nancy Graciano about an hour ago saying an all points distress call saying they needed another person. I was like, you know what? I'm doing absolutely nothing tonight. And I wrote an article today, so I have something to talk about. So.
Perfect. Awesome. All right. And let's see. We also got Michael Roderick. Hey, Michael.
Hello. Good to be back.
Nice to have you back. Hey, look at the little posters back there.
Thank you. Yeah, they've got the Exoplanet series. Still waiting on the Galaxy series. Everything's about exoplanets these days.
That's cool.
Oh yeah.
What's up with that?
For good reason, Michael. For good reason.
they could have a Galaxy series. All right. Well, before we get into our special guest, he's already ruined the surprise, but we'll just soldier on. Spoiler alert. So just want to give everyone a reminder that you should join the amazing community that supports this show, the WSH crew. They are our executive producers. They are our friends, our fans. They chat about space and astronomy during and after the show. And if you want more like-minded people to talk about space and astronomy, you should join this group. Go to wshcrew.space. All right, let's get into this week's special guest. We've got back as a return, Dr. David Kipping. David, welcome back.
Thanks. I didn't even know that I was the special guest. That feels like
you thought you were just
way too much of an honor than I deserve. That's nice. Thank you.
You are a special guest. How did you not know this?
It's just been one of those weeks, Fraser. I threw dinner down my throat like 5 minutes ago, came up to the call. It's like, what's going on? I'm here. I'm here to talk about space. That's all that matters.
Like you're in a mindset now that anyone could just like hand you tasks. Like, this is my job now. This is what I do.
Yeah. You just roll with the punches at this point, you know. But I'm glad to be here. Thanks for having me on.
For anyone who doesn't know, who are you? What do you do?
Okay, I'm a faculty member at Columbia University. I lead a team called the Cool Worlds Lab, and we look for planets outside the solar system and the search for life in the universe. And many of you might know me because I do a YouTube channel as well called Cool Worlds, named after our group. And on there, we talk about our research as well as just things about our place in the universe and things which fascinate me. And it's been a real fun ride to see that channel grow over the last few years and get to share the things which excite me about science.
Last time we talked, I think whether it was here on the Weekly Space Hangout or on my YouTube channel, I was really enthusiastic for the outreach that you're doing with the Cool Worlds Lab. And especially sort of connecting directly with the public on YouTube. And it's been now probably a couple of years since that, and the channel has grown leaps and bounds. How's that working out for you? Are you glad you have folded this additional enormous responsibility into everything that you do?
Yeah, it's definitely been more successful than I thought it would be. When I started the channel, actually my point of comparison was Ohio State University, and they had a YouTube channel, right. And it was like an Astro Coffee event, and they had 400 subscribers. I remember really clearly thinking, if I could get 400 subscribers, that would be crazy. That would be so ridiculous. And we actually hit that like within a couple of weeks. And then we stayed at a few thousand for a long time. I was feeling really excited about that at first, but then after a few years, I started to feel like, where's this going? This is taking up a lot of time. Is it worth it? And then I started to, I guess I sort of changed the style of the channel a little bit over time. And I think I stopped saying what I thought YouTube wanted to hear. And I started just being more myself, actually, and just talking about things which really I geek out on. And then things actually really turned around for the channel, which maybe isn't so surprising in hindsight. It is a responsibility because now, when you used to do a video with only 200 people watching, you didn't feel like it really mattered what you said, and you could really be more less thoughtful sometimes with what you said. And now you get like 1,000 comments on every little, you mispronounced that, or and I mispronounce things all the time, so people are always complaining about that in the videos.
Blame it on your accent.
And and of course my accent makes things extra confusing. And yet every single thing that you put in the video, I now have to really make sure is correct. Whereas, and before I was often just saying off the cuff, and now I'm really doing a lot of research into everything that goes into them. So it does take more time, but it's of course wonderful to have people who are willing to listen to you.
For me, shifting over to this sort of live model of doing things, posting stuff to the YouTube channel, responding to questions, getting your wrist slapped on a regular basis, has made me a way better journalist. Like I'm so much better at what I do now in terms of just being able to have this vast amount of information rattling around in my brain, being able to speak, I hope, intelligently as I go. Has this had a beneficial impact on your real job?
Oh yeah, absolutely. That's the thing that I think most research scientists might be surprised about. My research benefits in multiple ways by doing outreach. The first is that I'm often challenged to think about ideas which normally I don't spend a lot of time thinking about. If I was just doing exoplanet detection, which was pretty much my lane, until I started the Cool Worlds channel, I probably wouldn't spend that much time thinking about technosignatures or the astrobiology or the origins of life in the universe. But of course, those are the things which many people who are watching exoplanet videos are at a very deep level interested in. And so you get challenged to ask those questions and think about it more deeply. And so I forced myself, actually just an example happened just this last week. I'm sort of preparing in my mind a video about the Drake equation at the moment. It's been criticized over and over again, and I feel like some of the criticisms aren't valid. When you really read what Drake wrote in 1965, he actually had anticipated the limitations, which people often point out as criticism. And it's been like abused, and it gets a bad rap, but it's because of the abuse of the equation, not because of its original formulation. So I've sort of been thinking about this all in my head, and there's been different arguments about this, and I've been trying to reconcile them in my mind, and it actually led to me writing a short paper about it, a short research paper, where I found a way to sort of reconcile two statistical approaches to the Drake equation that I put on archive just a couple of nights ago. And so that'll undoubtedly form a piece of the video, but that wasn't an intent. It wasn't like, I'm going to make a video because it will lead to a paper, but that actually happens quite a lot, that whilst I'm like researching a topic very deeply, it inspires me to notice, actually, there's something missing in the literature. and this could be a useful thing to add. And so it's very synergistic, very synergistic activity.
And that was my suspicion, is that, you know, because you're the real deal, like an actual researching astronomer who is searching for planets, and you have all this knowledge and you advise all these students and you have this tremendous legacy of people that you work with, you understand the state of the literature and everything. And then at the same time, you're sort of out there you're also a YouTuber and experiencing the ideas and the thought and the pushback and the creativity that comes your way. Also probably the hate, I'm not sure. But the creativity that comes your way from the commenters. And for me, I'm just like, yeah, that is a fantastic question, and I have no idea. And for you probably can notice those gaps in the literature and say, that is a fantastic idea, and I know that nobody has asked it yet. And I also have the chops to do the whatever, perform a Monte Carlo analysis or make the Bayesian analysis to try and get at an answer to this. Are you getting more good research ideas from your work on YouTube than you can write papers about?
I definitely don't have enough hours in the day, I'd say that for sure.
Yeah, well, that's a whole other problem. Yeah.
Yeah.
But like too many good ideas.
Yeah, I think so. I mean, the thing is, a lot of these things that push me into these areas, which are maybe not traditional for certainly someone who's supposed to be working on exoplanets to be thinking about, that's a double-edged sword, right? Because there is a still, I don't know how to describe it, but almost some colleagues look down at SETI, for instance, and it's not a real science to be looking for aliens. Similarly for astrobiology, it's been, you don't have any data, so how can that even be a field of study? And then even more, I've even written papers, as you know, about ideas of interstellar travel, and as we were talking about when we started the show. So those things are definitely on the hairy edges of what's considered legitimate science in some circles, even though I think that's completely wrong that they're cast that way. And so I'm not a tenured professor, and I have to be a little bit careful about that, because I have to still put up a tenure case, and I can't have my tenure case be all I do is write papers about interstellar travel and aliens. Yeah. I have to maintain this theme, and I still love looking for exoplanets and exomoons. Of course, I still love that, but I probably don't work on those fringe ideas as much as I would actually probably enjoy doing so.
Wait for
and
tenure.
Maybe that's a good thing, actually, that I'm pushed back a little bit and I don't dive too deep. But there's, as much as I would love to dive deeper in that YouTube world of all of those questions that I know my viewers are so interested in, I am also an active researcher with a career in research, and so there's forces that balance during that process.
Yeah, and so what? Let's talk about the research side, because I think people are fairly familiar. I mean, seriously, if you want to see his more those ideas that we just talked about, the interstellar travel and the what's great is, you'll come up with an idea, you post a paper, and then you'll make a video to go along with it to help people understand what ideas you're trying to express. For your more sort of main research side, what are you investigating right now? What are you working on? Yeah,
so I tend to go in these like almost like the Intel TikTok cycle, where you have you develop something radically new, and then you like work on maybe the more mainstream, just improving things. So now I'm probably in that cycle of actually on the more traditional science side, I'd say from my perspective. We have this giant paper I've been working on for probably 4 or 5 years. I'm not even exaggerating. Since I think 2016, we started this paper, and it's just about coming to fruition. And it's been a search through all of Kepler's longest period Jupiter analogs, basically the planets which are most similar to Jupiter. Do any of them have moons? Which, of course, as many people probably who are familiar with my channel would know, that's something I'm very passionate about, is searching for exomoons. And so I can't spoil it, but that has been a huge effort to work through that. And we're right at the edge of finishing off the writing of the paper. And so we will submit it soon. It will go through the review, and I'm excited to finally get that off my chest. We also have this new technique for looking for exomoons that I published a couple of months ago that is based on looking at the wobbles of the planet. And it really highlights that these wobbles should have a very specific frequency pattern that hadn't been recognized before. In particular, they're undersampled. And so we would like to start looking for those. In fact, we've already started looking for those, and we have a couple of interesting candidates from that analysis. And so we have applied for some James Webb time to hopefully follow up some of these things. And then my most recent paper that's in review right now and has had a positive first review, so will probably be on the channel pretty soon, has been investigating what I call black swan events. So, and this kind of gets into Oumuamua and things like this, but very general. When you see a one-off event in astronomy, whatever it is, like a fast radio burst, the first pulsar, the first Tabby star, when you see that first, there's astronomers always are desperate to jump on that and be like, well, when are we going to see the number 2? And what is the underlying rate of these things? And what is the cost benefit analysis of continuing to look for these things in the face of ever more no's? I mean, should I keep going, or when do you cut your losses? And so I've written kind of a cost benefit and Bayesian approach to understanding black swan events in astronomy that is obviously very general beyond just exoplanets. And that's hopefully will be out pretty soon. So those have been like the 3 things on the research side I've been busy with lately.
Yeah, that's cool. I'm kind of amazed you're able to balance your time between them. But I mean, we're all stuck at home, nobody's traveling, so I'm finding I have a lot more time on my hands. Exomoons, like, right now we're fairly well, or we are gearing up quite nicely to be able to search for planets, for exoplanets, via transit, via the radial velocity method, even direct imaging. If you could create a special telescope for finding exomoons, would it have some capabilities that would be different from the kind of system that would be good for, would it be a coronagraph of a coronagraph? I'm trying to sort of imagine what special things you would need for an exomoon finder.
Yeah, I mean, it depends on the method. So you sort of hint there, maybe you were thinking of direct imaging in mind. And I think direct imaging is a very exciting approach for detecting exomoons. But that would be a very, very different telescope to the type of telescope you would use to, say, look for exomoons through gravitational microlensing, or which would probably be WFIRST. WFIRST is basically that telescope, to be honest. Or if you're going to build a telescope to look for moons through transits, which is primarily the method I use. So in that case, we're really looking to see the planets pass in front of the star. And if they have a moon, that moon should be trailing or ahead. And we should see another set of dips imprinted in the light curve that we can search for, as well as the wobbles of the planet itself. And so I normally think about what mission would I do for that. And Kepler and TESS aren't too far off what we want, but they were clearly lacking. So Kepler in particular was designed to find Earth-sized planets. Really, that was its goal. But there are no moons in the solar system which are Earth-size. So straight off the bat, that tells you it's going to be hard for Kepler to detect many moons, because it just really wasn't designed to find things as small as Ganymede or Io or Callisto. It's just not designed for that. There's like 1 or 2 stars that are bright enough for it to be lucky to catch that, but definitely not thousands that you'd want for a survey. So you want to up the aperture from the sort of apertures that TESS and Kepler have. Hubble is basically there at 2.5 meters. Kepler's 1 meter. James Webb's even better. You just want to collect a lot of photons. Yeah. We're never going to get an exomoons. Yeah. I mean, so I think we, if you have several size meter class telescopes, that's going to get you down to the precision to find sub-Earth size objects. And that would, of course, include planets as well, in that case, not just sub-Earth size moons. The other thing you really need is patience. You really need patience. This is one thing I'm somewhat apprehensive about with Plato. It's kind of Plato's another mission that's in the works for this, and it's still somewhat unclear exactly what their observing strategy will be. But if they were to go with one of the suggestions, which is to stare at one field for 2 years and then move to a different field and look at different stars, that would not be optimal in my book for the kind of work I'd like to do, which is exomoon hunting. I'd rather stare at the same stars for a very long time and monitor the dynamical interactions and trace those. It's very difficult with 2 years of data. If you're looking at the Earth pass in front of the sun, 2 transits, you can't look for wobbles with 2 transits. You need at least 3. Just mathematically, you need at least 3 to see a deviation from a straight line. You can always fit a straight line through 2 points. So you need at least 3 years of data, and even that's not really enough to get much statistical significance. So we'd like to see decade-long missions staring at these things. And maybe TESS might evolve into that. It's said that, George Ricker, when he talks about TESS, he's the PI of the TESS mission, often says that the rate at which it's using up its fuel is so little because it's in this unique orbit it's like locked into resonance with the moon. It's in a very stable orbit that it should be stable for decades in that orbit. As long as nothing fails on board, that means we could be collecting photometry of these stars for a very long time. And so that might then become the type of mission I would actually want for exomoons. So it might just be a game of waiting.
That's interesting. I sort of think of other creative ways, like there's this idea of the Lunar Farside Telescope, which would be able to find planets through the radio wave emission from their magnetosphere interacting with solar wind or solar events around other stars. And so you not only find a planet, but you also find a planet that's protected by a magnetosphere at the same time. And so when you sort of think about the kinds of conditions that are at Jupiter, the fact that or at that they're in resonance, or that they interact with the magnetosphere of Jupiter, or that at Saturn, say Saturn's rings are being generated by a moon, that there are specific conditions that maybe you could search for that it would make a bad planet hunting telescope, but a really good moon hunting telescope. But anyway,
but there's a whole literature of wonderfully imaginative ideas for exomoons, and that's why it's such a playground intellectually, and I think many of us are drawn to it. And some of those methods some of the methods have downsides in terms of the assumptions they have to make. And you kind of mentioned there like radio emission, and I'd say one of the ideas to look for exomoons is by basically cyclotron emission. So if you look at Io, it spews out all this particles into its upper atmosphere that then go very, very high up, of course, because there's so little gravity. And then those particles get accelerated on the field lines of Jupiter, and then that creates cyclotron emission. And so you could see that radio emission from several light years away. We're not talking tens of light years away, those. It's very, very limited in scope, even with unless you had like a lunar farside radio telescope, as you said. However, if you see cyclotron emission, does that prove you have an exomoon? Or could you think of some other mechanism that maybe doesn't operate in the solar system that could explain that? Another example people have proposed is thermal emission. So, and if you look at Io again, it's very hot because of tidal heating in its orbit. And so some people have suggested, why not look at these directly imaged planets? And if they have like a double bump in their spectrum, one bump from the warmth of the planet and then another bump from the warmth of a moon, and it's much hotter because it's being warmed, that could be a way to detect it. But it could also be maybe a disk around the planet. How do you know it's really a solid gravitationally collapsed moon? Especially if you're looking at these young systems, which we tend to with direct imaging, that are still in the process of forming. So there's lots of imaginative techniques for looking for exomoons. The challenge is often, is it ever going to be sufficient to slam dunk? And I think biosignatures are kind of analogous to that, because you can see a phosphine or ozone, but does that prove there's life on it? Or could you think of some other mechanism that might explain it? And we don't really have that issue with transits. With transits, it really is pretty crisp and clear if you see the dip of the moon.
Yeah, I mean, the whole phosphine thing has totally changed my thinking about biospheres, that we will never know for certain that there's life around another star. That, if we can't be certain about Venus, and it's right there. I don't want to take any more of your time. David, if people want to follow what you're working on, where should they go?
Well, they can check out the Cool Worlds channel. You can just, I think we're youtube.com/coolworldslab, but you can just Google Cool Worlds on YouTube. And you can also follow me on Twitter. I'm on David_Kipping. But YouTube's probably the easiest place to find me.
And if you're an aspiring astronomer and you want to attend Columbia, what's the process to join the Cool Worlds lab there?
Well, if you're an undergraduate at Columbia, we work with undergraduates all the time. We even work with high school students sometimes in the New York area. So reach out to me. And and if you're a graduate student, you should, you apply to graduate school, which we're just doing. We're in the process of trying to persuade graduate students to come to Columbia right now. Then that's obviously another way. So lots of different levels that you can work at the Cool Worlds.
Fantastic. Well, thank you so much for taking the time to chat with us today. Good luck in your hunt, and thank you for everything you're doing on the YouTube channel as well. Yeah, I know.
Thank you so much for having me.
Speak for everyone saying how much we appreciate that you make this bridge between the research work and the general public and helping people understand it. And we know it's a big sacrifice. So thank you.
It's my pleasure, and I'm grateful for people for tuning in. Honestly, that's the real pleasure. Thank you.
All right. Take care.
Bye.
All right. Let's move on with the space news. Michael Roderick, you're on my screen. Tell me what you got.
Unmute myself and track the blind. Okay. So, yes, new measurements of H naughts. So, trying to find Hubble's constant. So, this has been a source of attention for many years.
Use the words. The crisis in cosmology.
The crisis.
The crisis.
It's a nice alliteration there.
Yeah, it's perfect. I love it.
So, you've got kind of two groups. You got one group who's using Cepheids to measure the Hubble constant, and that's kind of led by Adam Rees and his group, and they're finding that the Hubble constant is about 73.2, and then you have the CMB group who's using things like Planck and WMAP, and their value is at 67.4. So you've got these two very discrepant numbers, which, of course, 10, 15 years ago, they were kind of on top of each other until we started getting better and better measurements with the CMB through Planck, and they've kind of started to diverge. So the thing that you really want then is to have another independent process which doesn't use Cepheids, which doesn't use the microwave background, to try to determine the Hubble constant. And there are several other ways that you can do this. The main thing is that you have to find the distance to another galaxy, and that's like the hardest thing in astronomy, is just trying to find distance to other objects. And so another group that I'll mention is led by Whitney Friedman. She uses the tip of the red giant branch stars to get distances to galaxies. Her value is at about 69, which is kind of like right in the middle between those two. And so we've got another way now to try to find distance to galaxies, and this is using surface brightness fluctuations in elliptical galaxies.
So how does it work?
So there are mainly two kinds of galaxies. You got spirals, you got ellipticals. We live in a spiral galaxy. It's got the nice spiral shape in it. Elliptical galaxies are kind of like a mess, a hodgepodge of stars, which are all kind of orbiting the center of the galaxy randomly. And so the trick here is that if you look at a nearby elliptical galaxy and you look far away from the center, if you look at this kind of diffuse light, that it will kind of appear bumpy because you're resolving little groups of stars. Farther out you go, those bumps will start to smooth away because it's farther out, you just can't see that structure. And so this group then is trying to use that kind of smoothness of these elliptical galaxies to get distances to about 63 galaxies in their survey.
So hold on, I just want to sort of make sure I understand this. So you're looking at a galaxy, and sort of the intrinsic brightness of where you can no longer see the galaxy in comparison to the central brighter core to it. And then you use that as a way to measure the distance.
It's not so much comparing it to the core, it's more of...
It's like where it fades away is telling you how far away it is.
Kind of, yeah. Where you can't see structure in the extended region of this galaxy. So they've always got these big clumps in the center, and then it kind of fades out as you go away. And so if you look in that region out there, kind of that extended region, the farther away you go, the smoother it looks, just because you can't physically resolve that structure.
Right.
So if there is, groups of stars in this little region here, you can't resolve that if it's far away. And so nearby stars are going to have, nearby galaxies are going to have more structure, far away ones won't. And so they go through the whole process, and we had 73.2 with Cepheids, we had 67 with CMB, and they get 73.3. So they are kind of leaning more towards the edge of the Cepheid variables. So it kind of throws more weight onto the Cepheid measurements and kind of adds a little more scrutiny to the CMB measurements. Do we really understand our physical models, which are predicting Hubble constant using the cosmic microwave background?
It's just dust.
Dust.
It's just dust.
So my last book saying 70 kilometers per megasecond per megaparsec, it's still kind of accurate. I think that was from Planck a couple of years ago.
Yeah. I mean, it's
not
in that range.
It's not
right?
out of date yet.
Yeah.
So Michael, what can we infer about dark matter or dark energy models? Are we in the right ballpark, or are we totally off base with what we think about the little that we think about dark matter or dark energy?
So it's interesting because there is actually another paper that came out as well, which is looking at dark energy itself. Are our models of dark energy correct? And so they model dark energy as kind of changing energy density through time. So early on in the universe, it had a different energy density than it did now, and then it changed, and their models seem to fit better the 70 megaparsec calculations that we're seeing now. So I think you've had multiple somewhat independent measurements disagree with the CMB measurements, and so it's now, okay, is the theory wrong? Do we have to go and adjust our physics? And I think we're starting to tweak that.
Well, hence the name, the crisis in cosmology.
Crisis, yes.
Yeah. So, I mean, from what I understand, the work on the Cepheid variables was really well done, very, very carefully done. Some of the best sort of pure scientific observations made. And the CMB model is, again, a very incredibly precise spacecraft that had one job and did its job very, very well. And the error bars definitely now do not overlap. It sounds to me like the galaxy brightness sort of tucks inside the error bars of the Cepheid variables.
Yes, and there was also another project which used lensed quasars, and they also were independent from the Cepheids and the other variations, and they also, I think, agreed with the Cepheids.
Gaia's been pinning down, the Gaia mission's been pinning down the Cepheid distance to a the error bars are way lower on that now, thanks to Gaia.
Yeah.
So it is interesting. It really does. Either the universe has been doing something weird in the interim between the cosmic microwave background and the more recent time, like it was changing its rate of expansion, or there's something wrong with probably the CMB at this point, the measurement. Dust. Yeah. Super interesting. I love it. I love this because, like, having these, it's a mystery that needs to be solved. And suddenly we get to hear each new piece of research, each new discovery. It pushes the evidence in one way, pushes the evidence in the other way. It's sort of the same thing, like what killed the dinosaurs, right? Was it volcanoes or was it an asteroid? And we get to hear each new piece of research. And I find this story absolutely fascinating. And I don't understand why it makes people mad. Like, they just want certainty.
We need an answer.
We want an answer.
There's always a definite answer in science.
Yeah. And science doesn't work that way.
Yeah.
It's sort of like the same thing with dark matter. Like, it was, it's only been recently discovered. Like, give astronomers time to figure out what it is and enjoy the ride. All of this stuff. Like, so anyway, yeah. All right. Thank you, Michael. Kimberly, tell me about super lasers.
I will. I will say I'm kind of jealous that cosmology gets a crisis, like a capital C crisis, because exoplanets don't really have anything like that. Like, there's the cosmology crisis, but there's not like exoplanet existentialism.
Is there a planet at Alpha Centauri?
No. who cares?
Okay. Oh, okay.
Whatever.
I see.
We did this last time I was here. I care more about the cool new developments in technology. Anyway, speaking of cool
Doesn't matter.
developments
Super
in
lasers are
technology.
going to be. So this is about the Death Star with its super laser, right?
No.
Oh, okay.
No. These are real super lasers.
Okay.
Anytime I can use super lasers in a story is awesome. Anytime I can use super lasers and exoplanets in a story at the same time, even better. Anyway, so this is a story about how the very teeny tiniest particles, minerals inside of a planet can determine the fate of the planet, and how we can use technology here on Earth to figure out what it might be. So our story starts actually back here on Earth, the only habitable planet that we know of. And there are a lot of factors that we think contribute to the fact that Earth is a good place for life. The magnetic field, which we've mentioned, helps protect us from harmful radiation. It keeps our atmosphere sort of in place from getting stripped away by solar winds generated by the molten iron core that we have. And we think that's a very important part of what makes a planet, might make a habitable planet. Similarly, plate tectonics probably plays a very big role in keeping the planet habitable over a long period of time, over a long enough period of time for life to develop and evolve. That is determined by how our mantle works, the layer between the core and the crust of the Earth, that sort of molten rock that flows and convects and shifts all of the crustal plates around. That's probably very important towards making a planet habitable too. And over the centuries that we've been doing, high precision geology and like geophysics, we've gotten a pretty good idea of how the Earth's mantle and core work and how that's related to the types of minerals that we have there, how the types of rocks and the components of these rocks, how they shift, how they mix, how they flow, how they transmit heat, how they can interact electromagnetically to do all the things that make Earth Earth. The problem is, or the opportunity is, now we know of thousands of other planets, many of which are rocky and many of which are a couple times larger and more massive than Earth. So what do the interiors of those planets look like? Big question mark. And the way you sort of start figuring that out is you start with Earth, which we think we have a pretty good handle on, and you scale that upwards. What is it, like 5 to 10 times as massive, 2 to 5 times as large. Scale it upwards. The problem is minerals behave very differently at the types of pressures that a planet that size and that mass would have in their mantles, in their cores. You'd get something like 3 to 5 times the pressure. It's like hundreds and hundreds of gigapascals of pressure inside what would be a super Earth. And at those pressures, minerals don't behave the same way as they do inside Earth's mantle. So how do they behave? How do we figure that out? That is an active area of research, and it's performed by there's 5 facilities in the world that have lasers powerful enough to shock minerals, rocks, to the types of pressures that you'd see inside a super Earth. And there's probably like 100 people around the world, maybe, who are researching this as part of planetary science and exoplanetary science.
Right.
So that's where this comes from. Recently, one of these groups used one of the facilities on American soil, the Omega Laser Facility, which is up in Rochester, New York, to shock one of the most common minerals that Earth has in its mantle. It's a component of a mineral called ferropericlase, for the geophysically minded among us. It's the second most common mineral in Earth's mantle. They shocked it up to super Earth mantle pressures with this laser to see what would happen. What does it do? How does this mineral behave? How would it behave inside of a super Earth? What they found is that it behaves very, very differently than it does inside Earth. And the important part is that it behaves differently than the other very common component of Earth's mantle does. So inside Earth, these two minerals, iron oxide, magnesium oxide, they behave pretty much the same. We have a pretty good handle on how they mix, how they flow, how they create, the homogeneous mix of our mantle, mostly homogeneous mix of our mantle. At super Earth pressures, though, those two minerals don't behave the same.
Huh.
The iron oxide, which is the one that they just tested recently, has a very dramatic drop in viscosity because it changes phase when the other one doesn't. And we didn't even know this phase existed until we decided to put iron oxide inside a super Earth, inside a laser.
Right.
And so what that means is that the mantle flow, the convection, the heat transport, the electromagnetic interactions inside the mantles of super Earths probably don't work like they do here on Earth. And we don't really know what it would be.
So, I mean, obviously there's a bunch of things that spring to mind, like having an internal dynamo that would help generate a magnetosphere, and having
internal dynamos, which we think are probably dominated by iron or some iron alloy.
Right.
If iron and iron alloys don't have the same physical phase, like material phase, like solid, liquid, gas, but there are so many other like crystalline forms that it can take, and that determines a lot of these fundamental properties about heat, about magnetism, about material transport. If that doesn't work the same, do they have liquid iron dynamos?
And so could you end up with a Goldilocks zone for planet mass to whether or not it's going to have an internal dynamo or plate tectonics? That's another question, right? Are you going to be able to have plate tectonics? It's almost like it gets so massive that it just seizes up inside.
It could, or it could have just an entirely fluid interior. So Earth has a solid iron core, and then outside of that, a liquid iron core, and then outside that, the mantle. There are different layers like that.
Right, and the liquid core is what generates the magnetosphere.
Exactly, but maybe inside super Earths, because this iron alloy, this iron mineral, is much more fluid, it's much less viscous than we thought it would be. Maybe it's entirely molten inside. Maybe there's a different type of layering or a different type of material separation than what we expect. So maybe super Earths are really great at magnetic fields because everything's molten.
Right. In fact, like a perfect magnetic field that could protect it from a really bad star. Like maybe it would work around a red dwarf. That's really interesting, huh?
Yeah, I find it.
It sounds like Kimberly, that we might actually be. I mean, we're a statistic of one, but we might be on the lower edge of that range, kind of, to have a magnetic dynamo.
It's totally possible. I mean, there's still so much we don't know about the magnetic fields of our own rocky planets in the solar system.
Like Venus doesn't really have one, and Venus isn't about our size.
Why doesn't Venus have one?
90% of
Mercury.
Earth.
What's up with Mercury?
Yeah.
We don't really fully understand how the rocky planets in our own solar systems and their magnetic fields work. And by doing these high pressure, high temperature experiments, these extreme condition experiments using these laser facilities, we're starting to better understand sort of the internal mechanics of planets that we can't really study in person.
I love that we can simulate them here on Earth.
It's pretty epic.
Yeah.
I did a lot of reporting on this last year about how we're using these facilities to, better understand Jupiter and Saturn and Uranus and Neptune. And it's really exciting to be able to then translate that to exoplanets as well. And like the behavior of the teeny tiniest little minerals, like have such planetary scale implications. It's very cool.
I wonder if there's going to be some kind of discovery in one of these processes going to go, oh, you know what? All exoplanets are uninhabitable, or all planets are habitable, or Earth is the worst planet, sort of like what Dave said.
Well, perhaps some people on the channel right now might remember a year or two ago, there was the discovery of a new type of protoplanet called a synestia. Or like maybe the moon went through this weird proto-synestia phase between, when it was formed and what it is now. And that was also based on discoveries at these high pressure laser facilities, based on how minerals interact under these sort of extreme shocked conditions. And so it's a whole different ball game
Yeah, that's
when
really
you get to
interesting.
those temperatures and those pressures.
Thank you, Kimberly.
Yeah.
All right, Dave Dickinson, not last but not least, what have you got for us?
Well, last week, Rocket Lab, I'm going to try to not say SpaceX and say Rocket Lab instead. CEO Peter Beck made an announcement that kind of surprised us that the company Rocket Lab's going to go somewhere where they said they weren't going to go, and
like
they're actually
he had to eat a hat
going to.
to
He ate his hat, like he said that if we ever build anything beyond Electron, which is actually quite a small, lightweight rocket launcher as far as rockets go. And they said that they're going to build what's called the neutron rocket. I guess proton is taken, so neutron is the next obvious thing that they're going to go to with a two-stage. It's about 75%, I think 50 to 75% of the payload for Falcon versus Falcon 9. So it's going to be a player in the medium lift capacity. But what's kind of interesting is this could do crewed launches as well, potentially, like Falcon 9. Now, this is something that they're looking for 2024. They're probably going to start launching. They're going to start launching out of NASA Wallops here next month. As a matter of fact, the pad is built, and we can see launches here from Virginia, from Norfolk, from Wallops. So Rocket Lab is about to begin with their second launch complex. They've been launching Electron, of course, out of New Zealand.
Yeah,
and it's interesting.
Is this the New Zealand astronaut corps up until this point?
I don't know if they're ever going to launch Neutron out of there. They were saying Neutron was going to be for the Wallops facility. And they're also talking about doing it, of course, for one thing they can put in that big payload fairing is more, for better or worse, more mega constellations a la OneWeb and Starlink and what we're seeing already going up now. Of course, this won't be until for a few years. It's interesting that Rocket Lab also is doing a merger that's going to go public here in the second physical quarter 2021. They're doing a $4.1 billion merger and going public right now. So they're going to actually be offering their stock public and live. This comes as they made this announcement kind of in tandem with that. So it's interesting that this is a large two-stage rocket. There's a lot of other companies like SpaceX, of course, is gearing up. There is a Avum, I believe, is launching out of Jacksonville this year. They're going to start doing remote drone satellite launches. There's also a company I wrote about, Blue Shift in Maine, that is going to start doing. They did their first suborbital launch of their Stardust rocket, but they have ambitions by 2023, 2024. I talked with Sasha Deary, the CEO for Blue Shift, and they want to actually do orbital polar launches off the coast of Maine once they have a site with a rocket called Red Dwarf, that maybe by 2023, 2024. So we're seeing a lot of private companies getting into the game. So it's going to be kind of an interesting time for spaceflight in the coming decade. Neutron will also launch the Capstone mission for NASA. Not Neutron, Electron, actually, this year. They're going to be launching the Capstone, which is the pathfinder for the lunar gateway that they want to put up. This is going to go in the same orbit around the moon, kind of as a proof of concept before they put Lunar Gateway and the crewed missions up there. This is a small CubeSat. They're going to do it with an Electron with a photon upper kick stage that they're using to put Rocket Lab actually had an interesting idea with Photon, and they demonstrated this last year, that if you've got that second stage, kick stage in there, why not build a satellite bus onto it? I don't know why more companies don't do that, because it's already there.
Yeah, and it's going to orbit.
So Photon basically has a Curie liquid stage engine on it, and it's got a satellite bus. So they demonstrated this last year. So they want to start going beyond low Earth orbit with Electron and start doing lunar missions later this year. There's actually a few different lunar missions that are coming up. Astrobiotics is sending a rover. Intuitive Machines is sending another rover. I think that's going on a Falcon 9. So there's a lot of lunar missions that we're going to be seeing this summer as well.
It's a really interesting time. Like in an alternate universe, if SpaceX had never developed the Starship, then we would see this really dynamic time of both SpaceX with the Falcons, but also, as you say, with the Electrons, with United Launch Alliance trying to sort of change the way they do things. Arianespace is pursuing reusable rocketry. It just goes on and on and on. And of course, Blue Origin. And so you've got this incredible dynamic, finally, this very dynamic launch provider, and they're driving costs down, and they're making a lot of really interesting payloads suddenly viable. But then you've got this just enormous literal shadow where it will still be cheaper to launch on Starship than to launch on an Electron, cheaper to launch on Starship than to launch on a Neutron. Like, it will be both.
There'll be a lot more to select out there as far as what you're going to
sure, but I mean, like, will you launch an Electron for whatever it costs, or will you go on a Starship for 1/10 the price? Like, if SpaceX can nail full reusable 2-stage rocketry, it makes every other launch system irrelevant.
I believe we're going to see Starship SN11 here in a week or so.
Yeah, I can't wait to watch it explode.
Up on the pad,
it's going to be beautiful.
Yeah. I turned off last week. I was like, okay,
no.
They landed it.
Yeah.
That was exciting enough. I was watching the SpaceX feed. So the SpaceX feed cut after they landed.
Yeah.
And that was amazing enough that we were like, they landed it. They actually landed it. So then I started seeing on Twitter, it's like, it took off again. And I'm like, what? It's like,
yeah, bold move. Elon Musk demonstrated rapid reusability and to fly again. Yeah.
They're very unscripted. So the Starship launches are always exciting to watch.
Yeah.
So you never know what's going to happen.
So what do you think? I mean, this is sort of pointless speculation, but do you think that there is a rocket market? I mean, is it a mistake to chase what
think so.
SpaceX used to do?
If you watch, there was a 60 Minutes interview, I think it was with Lori Garver, Sunday night. They were talking about, there's been an interesting discussion like with SLS versus Falcon Heavy, and do they really need 2 rockets? And there was a lot of interesting revelation from the behind the scene discussion with SpaceX and NASA about, if SLS was really necessary, that we have Falcon Heavy now there, and it can do those kind of missions that they need for Artemis. So, I guess you can never have too many, but it's interesting that, SLS is, and if you look at the launch cadence with SLS, it's my own opinion, it's a little depressing when you say, well, they're going to do a launch every other year. Yeah. I mean, Apollo did several launches per, they really had to sped up. You realize that 60s timeline was way sped up. I mean, they did several launches per year before to get up to Apollo 11. So to see that, well, SLS, the first one's not even going to have crew. Then maybe 2023 they'll have crew into a lunar flyby. It's like, it's the cadence is really slow with it.
Place your bets. How many do you think will fly?
SLS?
Yeah.
Well, what was the one we did before back in the 90s? Not
Constellation?
Ares, yeah. Remember they did do an Ares
the Ares
test
1
launch,
and the Ares 5,
We got excited with that because they did a suborbital launch, and we're like, okay, they actually have a rocket on the pad. Then they canceled Constellation.
Yes.
So, and with the change in administration, it seems like the new
3.
You vote 3? Okay.
I bet 3 SLS launches.
What do you think, David? Do you want the over on 3?
I'll say 2.
2?
All right. If we have one next
4.
year. It looks like next year we'll have our first one.
All right.
It's like
Michael, you get to be a tiebreaker on this one.
Ooh.
1.
How am
All
I
right.
the optimistic one about SLS?
No, I said 4.
Like...
I said 4. All right. So here we go.
Okay.
So just let history tell us. And nobody thinks there's going to be 5 and more, right?
I mean, I was very nervous when I was the most optimistic about SLS. I'm never the most optimistic about anything.
No, I know.
I think they're doing their green fire. Remember, they had the green fire test a few weeks ago when
they
they
announced
shut
the
down
new
early.
date.
I think it's coming up in a few weeks. They're going to do another hot fire.
Yeah. I saw the date. I forget the date, but yeah, it's quick.
It's coming up soon, within a month.
Yep. All right. Well, history will have to tell us what the actual number is. I look forward to reviewing this video in the future. We can see how many actually launch. I hope it's many. I hope it's thousands. All right.
Fraser owes us a present if we guessed correctly.
Sure, absolutely.
Future Fraser.
All right.
Listen.
All right. Someone keep track of this, and we'll figure out some special prize.
Remind Fraser in like 5 years what he promised us.
What it should be is that we get to hang out in person at some event, and I will, I will definitely buy the winner dinner at the very least. Yeah, that's the key, is that we get to hang out in life again.
It'd be great to be able to go see rocket launches again, like up close.
Yeah. All right, Dave, you're on my screen. Tell us what you're working on, where people can find out more.
Still writing for Universe Today, Sky and Telescope. Still have my second book out there. Like I said, the Hubble constant is still kind of accurate in it right now. When there's a very basic, before we get into the sky watching bit in there, rundown of astrophysics and what you're actually looking at. Just a very basic chapter in there. So that book is out there, and I'm actually writing for Mike Simmons' Astro Gear today. I should have a set of giant binoculars from Edmund Explore Scientific. That's going to be a very interesting review that I'm going to be doing.
What's the aperture on them?
These are like 120 millimeters. They're tripod mounted.
Oh,
so
wow.
They're pretty good size. Yeah, I'm excited to review those. So you got to do that whole get the gear, request the gear, get the gear here, hope the skies are clear. There's a long tail to do it. Reviews are fun, but there's a long tail to doing it.
It's why I just never do them, or it's why I foist them off on you, because
it's fun to do.
The Canadian border adds a whole other level of misery because, I have to sign tax forms to be able to.
Oh, that's true. I never thought of that.
Oh, it's misery. Yeah. I even have to write checks sometimes that I then get back at the end of the year because I have to pay tax on the value of a telescope when it crosses the border. So no.
Wow.
Yeah. It's just not worth it.
Yeah. I just get UPS to come to the door and pick it up.
Yeah. I know.
Put it back in the box.
Within the same country. Yeah. No, it's next level. Astro Guys with a Z on all the things.
Yes.
Awesome. Kimberly.
Hey. I just wrote an article about these super lasers and super Earth mantles, which you can find on eos.org. And I just talked to the scientist behind the NASA project that exploded a giant thing of water in the upper atmosphere.
Nice.
I just talked to him today, and it was super, super cool. They're creating artificial clouds to basically study how the upper atmosphere works. There was also a whole thing about rocket emissions that I'm probably not going to go into because the atmosphere is way cooler than rockets. Sorry.
Right.
But that will also be up on eos.org at some point soon. And I'm also on Twitter at AstroKimCartier.
Perfect. Michael.
I'm on Twitter at Michael Roderick. And on March 22nd, we have another Astronomy on Tap coming up. So if you liked our talk about the crisis in cosmology, we are going to be talking more about the tension between the Cepheids and the CMB. And we also have another speaker who's going to tell us about dark matter detection, direct dark matter detection, which is going at my institution at Penn State. So check us out on March 22nd.
Fantastic. As I mentioned, I had a fascinating interview with Christopher Morrison from USNC, and they're working on a mission concept for retrieving a sample from an interstellar asteroid or comet. So you may want to come over to my YouTube channel and watch that. And of course, Universe Today on all the things. All right, I'm going to put you guys all back in that view. Thank you, everybody, for joining us here on the Weekly Space Hangout. We really appreciate you spending the time with us every week. Thank you to all of the moderators and everyone in the chat who's keeping things fun and active and asking all these great questions that I never get a chance to get to. I apologize. And thanks to my co-hosts for bringing all their knowledge and, of course, our special guest. And we will see all of you next week. I have no idea who our guest is next week. Anyway, I'm sure it'll be fun. Thanks, everybody. Press the button.